Hi AP Calculus students, how you doing? Miss Culver here in our living room. We are working on section 2.1b today. This is called differentiability. This is how I abbreviate it so I don't have to keep writing it. Derivatives, that's how I abbreviate it. And continuity, which we've already abbreviated with a C. What you're going to find today with 2.1b, it is one of the last sections you'll come across that is very based on symbols and concepts. After this, in section 2.2, we're going to be using some really cool simple rules that come from all this more difficult work. So this is kind of the end of the hard stuff for a little bit. So let's take a look at what we're going to be doing. Number one, we're talking about derivatives and differentiability. Differentiable at a point, meaning having a derivative, or saying that f of x is differentiable at a point means. So, before we look at this, I just want to say I've been leading up to the idea. We have been using difference quotients and different formulas to find what would be the limit as delta x approaches 0 of a slope formula, right? We've done this over and over. And in other words, what we've been doing is finding the slope infinitely close to one point. That now is called a derivative. That's what we're going to start calling it. The slope at one point is a derivative. How do we show it? We show it with a tangent line, like right here. There's one point, there's a tangent line through it, and you can see that this purple line has a slope. That slope would be its derivative. Okay, so that's the terminology we're going to start using. So if a point has a derivative located there, that means that the limit as x approaches that c from the left, right, exists. Notice this is a slope formula, the alternative form, and it equals the limit as x approaches c from the right of the same slope formula. This would mean that the slope, as you approach an x of c from the left and the right, is approaching the same slope. That makes it differentiable. So notice these limits are the alternative form of finding a slope at one point that we've used before. Now we will call this a derivative, as I have said. So we're in blue here. If the slope or derivative is the same from the left and right of c, then the derivative at x equals c exists. A function is not differentiable or does not have a derivative at x equals c if there is a sharp corner there because the slopes are not the same as you approach from the left and the right of your x value. We're going to see what that looks like. Number two, more important than you would think, is that if a function has a derivative at x equals c, again, the slope is the same from the left and the right of that value, the function is automatically continuous at x equals c. Let's stop here for a minute and then we'll talk about why. So what this means is, when they talk on the AP exam about a function being differentiable, even though they don't say it, it also means it's continuous because these conditions are met. F of c must exist. It is used in the limits above. Take a look in these slope formulas. F of c is used, so it passes the first part of the continuity test. That point has to exist for you to find these limits. B, the limit as x approaches c of f of x must exist for the same reason. Again, notice according to properties, I could take the limit of the numerator separately with the limit of the denominator, meaning the limit as x approaches c of f of x must exist. That's the only way I'm going to find these limits. And c, those two, 1 and 2, must be the same. If you are approaching the same x value, sloping towards it, then it must be that it also hits it at that point. That point has to exist. So, number 3, also very important, differentiable implies continuity, but continuity alone does not imply that it's differentiable. Let's take a look at why. Here's a graph of f of x equals x squared. Notice that this is a continuous function. This is the first time we're going to look to say that it's also differentiable. What do I mean by that? That it has the same derivative from the left and the right of x equals 0 in this case. What I did to help you see that is a derivative is a slope at one point, so I drew little red tangent lines at different points on this graph. So notice where x equals 0, that little tangent line has a slope of 0. Notice from the right of x equals 0, these little tangent lines all have a positive slope, but they are becoming less and less steep as you approach x equals 0. Those slopes are approaching 0. Let's go to the left of x equals 0. Let's look at those tangent lines. Notice that they all have a negative slope, but as x approaches 0, they are becoming less negative and approaching a slope of 0. So this function is differentiable at x equals 0, and so it's also continuous. Let's take a look over here. This is the graph of the absolute value function. It is not differentiable at x equals 0. Let's take a look why. You know that in an absolute value formula, that to the right of 0, that this line has a slope of 1, and to the left of 0, this line has a slope of -1. So this function is not differentiable at x equals 0 because as you approach from the left and the right, the slopes are not equal. It is 1 on the right, -1 on the left. However, without a doubt, this function is continuous, right? At every single x value, there's a y value, right? And as you approach each x value, the y values exist. There's a limit as you approach each x value. So, differentiable and so continuous. Not differentiable, but it's still continuous. So that's the reason I wrote over here, ask me about the square and a rectangle. It's exactly the same idea that a square is always a rectangle because it meets all the conditions, but a rectangle isn't always a square. So if a function is differentiable, it's always continuous, but just because it's continuous doesn't always mean it's differentiable. Let's go over to number 4. How might this look on the AP exam? It is important to remember on your own that differentiable implies continuous also. They won't say that. It has to come to your mind. Without it, you will not be able to do 2 to 4 of the problems. There will be multiple choice problems that talk about differentiability and continuity, and so you have to pull both those ideas in. Also, you will use the idea that continuous does not imply differentiability on the AP exam. So we have to be clear about that idea. So let's try some example problems. I don't think you've ever seen anything like this before. So I'm going to show you the techniques I use to help myself. Here's our example problem first, number 40. I didn't write the actual question. What they wanted you to make was a derivative graph, which you've never heard of before. So I'll write that. What is it that we're actually doing? We are making the derivative graph for the function that was given. That's our job. Okay. So once you have a graph, what is a derivative graph? What a derivative graph does, and I'm going to do that in red, is that every x on this graph, we are going to make a little tangent line, see about what that slope is, and then we are at that x going to record that slope and then connect those points. Let's start at the most obvious place. Here's where x equals 0. If I drew myself a little tangent line right there, notice its derivative would be 0, the slope at one point. So where this x is, I'm going to record a y value of 0 for the slope. Let's go to where x equals 1. On the graph, I'm going to draw myself a little tangent line. Notice that that tangent line is positive, fairly steep, maybe like around 1 or 2. So that would mean at an x of 1, I'm going to record, let's call it a slope of 2, somewhere between 1 and 2. I'm going to record the point 1, 2. Let's go over to where x is 2. Let's go up. Let's make a little tangent line to help ourselves out. Notice that that tangent line looks very steep and positive, somewhere 4 or 5. So on my derivative graph where x equals 2, I'm going to record a y value of, how about 5? There we go, 2 and 5. There we go. Okay, let's go to the left of 0. Let's go to where x is negative 1. I'm going to draw a little tangent line to help myself. That slope is definitely negative, maybe around negative 2. So for this x value of negative 1, I am going to record a y value of negative 2 for the slope that I see, right? Notice it's just a sketch. I'm not being entirely about what exactly is that slope. So that's 1, negative 2. Notice where x is negative 2, if I drew the a tangent line there, much more, still negative and much steeper. So how about if we call that a negative 2 and maybe a negative 5 slope. So on my derivative graph, where x is negative 2, I'm going to record a negative 5. There we go. See these red points? I'm going to connect them, and that makes the derivative graph. That's supposed to be a straight line. That's just my bad drawing. There we go. That is your first derivative graph. I want to point out to you, remember when we were using the difference quotient to find the slope at one point, that what we were finding is that when we had an equation like 3x squared, that we could bring the exponent out front, multiply it, and reduce the exponent by 1. Not sure if you remember that. Take a look here. This is obviously an x squared shape, and our derivative graph is a line which is to the first power. Notice that exponent did reduce by 1 from the original graph to the derivative graph. Number 44. They are asking, they said that there is a tangent line to h of x. Now notice in blue I made a possible h of x. There's an infinite number of pictures I could have drawn for a graph in blue here. The conditions they gave was there's a tangent line to h of x at negative 1, 4. Notice I just made pictures of what they had. And they said that that tangent line passes through the point 3, 6. So notice I made that happen. Okay, so I made a possible function. I made a tangent line that met their conditions. And now what they want is they said find h of negative 1. Okay, well, take a look. On my function h, I'm going to go to where x is negative 1. Is there a point there? There sure is. It's negative 1, 4. So there we go. H of negative 1 is a 4. That's the value of that blue function there. Now they're going to ask for, this is called the derivative of h at negative 1. That's our derivative symbol for finding the slope at one point. That is the slope of a tangent line. So they want to know, what is the slope of this function where x equals negative 1? Let's go there. There we go. Well, if I wait, there's a tangent line there. So in other words, at this point on the curve of this blue graph, there's a tangent line there, and the derivative is the slope of that tangent line. And if you look here, there you go. I know how to find the slope of that tangent line. I've got 2 points. Here we go. y2 minus y1 over x2 minus x1. Here we go. That's going to be a 2/4 or a 1/2. There we go. Next, we are going to graph another derivative graph. This one's a little harder. I knew you'd need a little practice here. Here is a graph, and we are going to sketch the derivative graph again in red. So let's take a look. My obvious place to start is at 0. But when I look here, I can't really draw a tangent line. I could draw a tangent line up and down. I could make one across. If you notice, there are a ton of tangent lines I could draw at this point. And that is because there's not a derivative at this point. There's not a slope, because as you approach x equals 0 from the right, this is a positive derivative, and as you approach x equals 0 from the left, that is a negative. The slope is not the same from the left and right of x equals 0, and so there's not a derivative there. So you may be like, well, if I have to make a derivative graph, how do I record a point at x equals 0? I can't. So this is, my derivative graph is going to be undefined at 0. So that's going to be our hardest spot. So let's move along. Let's go to the right first and see if we can help ourselves out. I'm going to draw a few different tangent lines and see what is going on with the slope. Right? So here's a tangent line, very steep and positive. Here's a tangent line, still positive, less steep. Still positive, even less steep. Notice you can kind of see what is happening here to the right of 0. For this x close to 0, I'm going to record a y value that is positive, very positive, and of high value. As I go along to the right on the x-axis, for each of these x's, I'm going to record a y value showing that the y's are positive, but getting closer and closer to 0, they are getting less positive towards 0. Okay, so bear with me here. Here's going to be my sketch. And let's see if I actually made that happen. Notice where x is 0, not defined, my derivative graph. Notice where x is very close to 0 on the right. Take a look at that. That y is positive and has a high value. Take a look at this x right here. Notice that the y is positive, but not as high a value as here. So notice that my y values are all positive for these x's, but are getting closer and closer to 0, just like my slopes are. Let's go to the left of 0 here. Let's draw ourselves little tangent lines so we can see what's going on. Notice that this tangent line here, negative, as I get closer to where x equals 0, notice here, they are becoming more and more negative at these x's. The slopes are becoming more negative, so that's the y values I am going to record. Okay. Notice that, again, I have to make sure that I don't have a point recorded on my derivative graph where x equals 0. Let's see. Here's what I'm going to draw. If you're confused, I totally get it. I'm a calculus teacher. I'm used to this. Let's see, though, if what I drew works with what we see. Where x is 0, I do not have a derivative recorded because we said there isn't one. Just to the left of 0, this tangent line seems to have a very steep negative slope, and if you take a look, I have recorded a very negative y value. Let's go to this x right here. Again, a negative slope, but not as negative as we were. Here we go. Again, a negative y value here, but not as negative as here, right? And as we go out, notice that these slopes are approaching to flatten out towards 0, and so I made my derivative graph do the same. So this takes practice, but draw yourself little tangent lines to help you. My derivative graph is in red. Last problem. This is on the graphing calculator. I already put this function on a y1. They want us to graph this function and the derivative function and describe the relationship. So here we go. I already put on a y equals the function that they gave me. Let's just hit a zoom 6, take a look at it, and I will put that on the board in black. Okay, let's take a look. That looks about like this. Now, the reason why I picked this problem is I want to show you how to graph a derivative graph. So let's go back to our y equals. Let's go to y2. And I want the derivative of the function I put into y1. So we're going to hit our math button on the left and go down to end derivative. Here we go. We've used this before. I'm going to put an x in that denominator. Now I could retype the function here, but I already put it in y1. So I want to really just put in y1 in parentheses because it's easier. Here's how you do that. Okay, we're going to hit our variables button. Here's your variables. Notice top right, they are the y variables, and we are graphing functions. There we go. Now I can just choose y1 instead of having to retype everything in y1. What x's do I want to see? All of them, so I'm going to put x equals x. Now let's go ahead. I'm going to go back a little bit to the left of the y2 and just hit enter and make it a little darker so that you can see which graph is the derivative graph. Let's go ahead and graph it. It's taking a minute. Even the calculator takes a while to really think about it. There we go. So let's go ahead and draw that graph in red. Okay, just giving myself some points to help me out here. Okay, here's the derivative graph here that we had on our calculator. Let's look at it. So let's circle it in red. Notice that our original graph in black is cubic, and the derivative graph is a parabola, so would be a degree of x squared. Again, we've reduced that exponent by 1. We're seeing that a lot. Okay, let's look in purple at a couple things here. If I can find a purple, I can. Okay, let's actually make tangent lines to help ourselves on the original function. I'm getting a little sloppy. There we go. I just want to point out a couple important things. Take a look at the top of this graph here. If I drew a tangent line, it would have a slope of 0, and sure enough, let's go right down here to the x. Sure enough, that's the point 0, 0. At this x, it recorded a slope of 0, a y value of 0 on the derivative graph. Let's go down here. This is a minimum point. If you drew a tangent line, it also has a slope of 0. Let's go up to that x. Sure enough, on the derivative graph at this x, that is the point, the x is some x and a y value of 0. Again, recording a slope of 0 for the y at that x. Let's look to the left here. Let's look right here. Notice that these slopes are definitely positive and becoming less positive. And sure enough, our derivative graph is recording all positive y's approaching 0. In between here, take a look at these slopes. Notice that they start at 0, become more and more negative, and then start to approach 0 again. Notice that's what our derivative graph did. Negative y's, very negative, and now they're still negative but approaching back to 0. Let's look on the last part of our graph. These tangent lines are all positive again and getting more positive as x gets bigger, and that's what our y's are doing. These are positive y's recording the slope, and they are becoming more positive. And that's why the graph looks like it does. And that is it for section 2.1b. It takes some practice. I know you can do it.